So in this video we want to introduce the idea of polar coordinates or polar coordinate system. And the reason for introducing a new coordinate system is that sometimes it's easier or more convenient to do calculus in a coordinate system other than the Cartesian or rectangular coordinate system. So over the next few videos we'll be exploring different coordinate systems and looking at calculus in the context of those coordinate systems. So the idea behind, and I still have an R there, I don't know why, but the idea behind the polar coordinate system is to construct one. All you do is any place you want in the plane, you establish an origin or a pole. So they also call this the pole. And then from that pole, in any direction you want, you make a polar axis. So this is a directed axis moving outwards from the pole. And then to represent any point you want in the plane. So for example, if I want to represent this point where I've established this origin or pole and this polar axis, if I want to represent this point, I do a directed line segment from the origin to the point. So you can kind of think of it as being a vector if you like to think about vectors. And then what we do is measure the length of that directed line segment, and it's typical to call it R for radius. And then we measure the angle from the polar axis to that directed line segment, the angle theta from the polar axis to the directed line segment. And then we represent the point in terms of the radius and the angle with respect to the polar axis. And it turns out this is sufficient information to completely characterize this point in the plane. So an example in the next slide, let's say and it's what's going to be convenient for us to do is to establish a polar coordinate system over top of an existing rectangular coordinate system. So think if you had XY axes, you impose a polar coordinate system over that set of XY axes by letting the origin, the Cartesian origin, to also be the polar origin, and then letting the positive x-axis be the radial axis. And then we can think about things in terms of what we learned in geometry: 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians. And we want to think about the polar coordinate system as kind of being a set of concentric circles centered at the pole or the origin. And then you shoot radial lines out from the origin, and you can make graph paper with radial lines and concentric circles. So what I mean by that is, if I keep my changes so far, if you just go into Google, for example, you can Google radial or polar graph paper, and that's what they're going to give you is graph paper where we've centered ourselves at a pole and sent radial lines out intersecting concentric circles that are centered at the pole. And so that's kind of how you want to visualize it. But we can completely impose a Cartesian a polar coordinate system over top of an existing coordinate system, and then map back and forth between the rectangular coordinate system and the polar coordinate system. So in this case, I have circles of radii 1, 2, 3, and 4 centered at the pole. And I have this point here that has this directed line segment has a radius of 4. And the angle that it makes with respect to the polar axis, or the positive x-axis, if I want to think about it that way, is pi over 6 radians. So I represent the point r theta with its radius and its angle. We do this using the same convention we do in trigonometry, where a positive angle represents a counterclockwise rotation and a negative angle represents a clockwise rotation. So same convention that we have from calculus. And what we want to identify is, from our background in calculus, is that this the polar representation of a point in the plane isn't going to be unique, because we have coterminal angles. So for example, if we start here at the positive x or the radial axis and we rotate around 360 degrees or 2 pi radians, we can continue through and wind up at the line again. So in other words, we know that pi over 6 plus 2 pi, which is the same as 12 pi over 6, equals 13 pi over 6. We know that 13 pi over 6 is coterminal with pi over 6. So we could represent this point as 4 comma 13 pi over 6. We could also rotate the opposite direction. So if I started at pi over 6 and I subtracted 2 pi, I could rotate around and have a negative angle representing that point. So this angle here, because there are infinitely many angles coterminal with pi over 6, this isn't going to have a unique representation. In fact, we could say, hey, this point is going to be kind of equivalent to 4, the radius, comma, and then we could do pi over 6, which is the simplest angle with respect to the radial axis, but we could add any 2 pi k to pi over 6, where k just has to be some integer value, and we would get a coterminal angle. So there isn't a unique representation, but it's probably more typical to represent a point using an angle between 0 and 2 pi, or 0 and 360 degrees. The other thing that's a little less intuitive is if I reflect this point through the origin over to here, we could also represent this point thinking about the point here on the other side. So let's say I have a radius, let's say I have the angle that sweeps me through to here. So sweeping through from the radial axis to here. And so what's that angle going to be? We're in pi over 6 world. So rotating around to pi would be negative 6 pi over 6, which reduces to negative pi, that counterclockwise rotation. So this angle right here would be an angle of negative pi over 6. So you could think about swinging through to this point here. This point would be the point, radius is 4. The angle is negative 5 pi over 6. So if we negated this 4, so we do negative 4 comma negative 5 pi over 6, that would actually reflect us back through the origin and be another way of representing this point. Kind of a non-standard way of representing it, but it's also a representation of the point, negative 5 pi over 6. The idea is rotate 180 degrees out so you get a reflection through the origin, and then negate the radius to bounce yourself or reflect yourself back through the origin to that point. Reflection through the origin is the same as a 180 degree representation. So that's a basic overview of polar coordinates, and then we'll go more in depth in subsequent videos.